Welcome. Today, we're going to decode the language of chemistry. We're taking three huge ideas, moles, solutions, and reactions, and we're going to move them out of the textbook and into the real world, showing you the practical skills you actually need in the lab. Let's jump right in.
So this is the big question, right? Figuring out what a mole is, that's the aha moment for so many people in chemistry. As soon as you get it, suddenly everything from mixing solutions to predicting how a reaction will turn out just clicks. It's the one key that unlocks all the math in chemistry.
So here's our game plan. We'll start with what I like to call the chemist's dozen, the mole. Then we'll see how to use moles to understand solutions and figure out what happens in reactions. And finally, we'll see how it all plays out in the lab. It's a straight line from an idea to actually doing something with it.
All right, first up, we've got to build our foundation, the mole. And trust me, this isn't just some random term you have to memorize for a test. It's like the alphabet of chemistry. You nail this, and I promise, everything else we talk about today is going to fall right into place.
So what in the world is a mole anyway? Don't let the weird name throw you. It's just a number, a quantity, kind of like how a dozen means you have 12 of something. The only real difference is that a mole is a ridiculously huge number. We're talking about 600 billion trillion. And why so big? Because atoms are just that tiny. So think of it as the chemist's special dozen for counting particles. Now check this out. The mole is like a central meeting point. See how there are different ways to get there? It doesn't matter if you're weighing a solid, measuring a gas, or mixing a liquid. There's a specific formula, a specific path to figure out how many moles you have. It's the one thing that connects all different kinds of matter. Okay, time to put this to the test with a classic problem. Let's say you've got 1 tiny milliliter of alcohol. You know its density, and you know its molar mass. So the question is, how do you use those pieces of information to figure out the actual number of moles in there? So, how do we crack this? Well, first things first, we need the mass, but the problem only gives us volume and density. No big deal. We know that mass is just density times volume. Once we have that, we can use our go-to formula, moles equals mass divided by molar mass. Or, as you see here, we can just smash it all into one step, plug in our numbers, and this is the beautiful part, the units cancel out perfectly, leaving us with our answer in moles. Okay, so now we have a way to count particles using the mole. What's the next logical step? Well, let's see how this idea helps us when we're dealing with solutions, which is really all about measuring how much stuff is dissolved in a liquid. You know, when we talk about how strong a solution is, we're usually talking about its concentration. And there are two main ways to think about it. There's molar concentration, which is how many moles of stuff are in each liter. Yep, that's our chemist's dozen again. Or you can have mass concentration, which is just how many grams are in each liter. One is about counting, the other is about weighing. And the best part is, it's super easy to switch between them. Molar mass is basically the magic bridge that connects molar concentration, counting the particles, and mass concentration, which is just weighing them. It's a really simple formula that lets you jump back and forth between the two whenever you need to.
Okay, now we get to where the mole really shows its power. This is where we move beyond just mixing chemicals and start being able to predict exactly what's going to happen. Honestly, when you understand moles and reactions, it's almost like having the recipe for how the universe works.
A balanced chemical equation is basically just a recipe. You see those numbers in front of each chemical? Those are called stoichiometric coefficients, and they tell you the exact ratio of your ingredients. So for every A moles of substance A, you need B moles of substance B. This recipe is always written in moles, never in grams or liters.
Let's think about making grilled cheese sandwiches for a second. If your recipe is 2 slices of bread for every 1 slice of cheese, and you have exactly that ratio, say 10 slices of bread and 5 slices of cheese, that's a stoichiometric mixture. You'll use everything up perfectly. But what if you have 20 slices of bread and only 5 slices of cheese? That's a non-stoichiometric mixture. You're definitely going to run out of cheese first.
So that ingredient you run out of first, in our case, the cheese, has a special name. It's the limiting reactant. And this is a super important idea, because the limiting reactant is the boss. It's the thing that decides how much product you can possibly make. Once it's gone, the reaction grinds to a halt, no matter how much bread you have left over.
All right, enough with the theory. Let's get our hands dirty. Let's take all this stuff, moles, concentration, limiting reactants, and see how it all comes to life with a couple of fundamental lab techniques. Let's start with something you'll do all the time in a lab, dilution. That's just when you take a really concentrated solution and make it weaker by adding water. To do it right, you need the right tools.
The volumetric pipette on the left lets you grab an exact amount to start with, and the volumetric flask on the right makes sure your final volume is absolutely perfect.
And the procedure itself? It's actually really straightforward and kind of satisfying. You use the pipette to pull up your starting liquid, transfer it into the flask, and then you add distilled water exactly to that tiny little line etched on the neck. Cap it, give it a few shakes to mix it all up, and you're done. You've just made a perfect dilution.
You know, the idea behind this is so simple, but so powerful. When you dilute a solution, you're not changing the amount of dissolved stuff. The number of moles you started with is the exact same number of moles you end with. All you did was add more water. And that simple fact gives us this incredibly useful equation. C0 V0 equals C1 V1.
And for our grand finale, we have titration. This is basically chemical detective work. As you can see in the setup, you use a solution where you know the concentration. That's in the tall glass tube called a burette, and you use it to figure out the unknown concentration of another solution down in the flask.
Now, you can't just use any old reaction for a titration. It's got to tick 3 boxes. It has to be complete, meaning it goes all the way to the finish line. It has to be fast, so it happens pretty much instantly. And it needs to be unique, meaning there are no weird side reactions happening that could mess up your results.
So, what's the whole point of a titration? You're hunting for one very specific moment, the equivalence point. This is that perfect moment we talked about earlier, that perfect stoichiometric ratio, where the moles of the chemical you've added from the top exactly match the moles of the chemical in the flask. The reaction is perfectly finished. But you're dealing with clear liquids, right? How can you possibly see that invisible moment? Well, you add a special chemical called an indicator that changes color. This quote describes that moment perfectly. You're adding your solution drop by drop by drop until one final drop makes the whole thing change color and stay that color. That's your signal.
And once you've found that exact volume, the moment the color changed, bam, you've got everything you need. This formula right here ties it all together. The concentrations, the volumes, and that mole ratio from the balanced equation. You just plug in everything you know and you can solve for the one thing you don't, that mystery concentration.
So, you can now predict what happens in a reaction. That's huge. But what's the next level? It's taking control. How could you change things like temperature or pressure to speed a reaction up, slow it down, or even change what you end up with? Well, that's where we get into things like kinetics and equilibrium, but that's a story for another time.